Okay, so now that you've had some experience looking at the basic properties of rings, we're going to look at some very familiar concepts, actually, zero divisors and units. And they're going to work very similarly as they did with some of our other number systems. So just to remind you about how these things work, we're going to review how multiplication involving zero works. We're going to define what zero divisors are in rings now. We're going to review how the concept of inverse works. Then we're going to define what a multiplicative inverse is in rings. Then we're going to define units in rings. And then finally, we're going to look at zero divisors and units in our example rings. All right, so let's get started. There are two important facts about multiplication and zero. If R is a ring and we have two elements A and B in our ring, when we multiply by 0, we get 0. So A times 0 equals 0. And actually, there are two ways that we can multiply by 0. Yeah, we can multiply by 0 on the left as well. And it happens to work out that 0 times A also equals 0. It is possible that we can multiply two numbers A times B equals 0, but A and B themselves are not 0. And when that happens, we get zero divisors. So let R be a ring. We say that A and R is a zero divisor if A itself is non-zero. There is some B in the ring with B non-zero, such that either A times B equals 0 or B times A equals 0. Again, we got to do multiplication both ways in case the commutative property does not hold for multiplication. And notice that in this case, the B that goes along with A, that is also a zero divisor. All right, so let's consider some of our examples of rings and see if they have any zero divisors in them. So if we look at the integers, the even numbers, the rational numbers, the complex numbers, even z sub p, where p is a prime number, those all have no zero divisors. We have already proved that for these rings, or in the case of zp, you are going to prove that in one of your portfolio problems. So what that means, of course, is that whenever I have two elements of those rings multiplied together to give me 0, that means either A is 0 or B is 0. One of the things multiplied is going to be 0. However, that was not true for rings like Z6. There, if I did 2 times 3, you get 6, but 6 is the same as 0 in Z6. In the matrices, I'm going to look at 2 by 2 matrices. If you tweak things around a little bit, it's easy to find two non-zero matrices that multiply to give you 0. Here's an example that I give here. In fact, here's a fun fact. Anytime you have a matrix that is not invertible, that happens to be a zero divisor. All right, so if we look at P5, and remember P5 is the power set of a set with 5 elements. That has zero divisors as well, but let's remember how addition and multiplication work. Addition, when you're adding two sets together, you're taking the union and then removing the intersection. And when you're and so that means our additive identity is going to be the empty set. And also remember that multiplication is intersection. So that means if I multiply the two sets A, B, C times the set containing D and E, and those are in P5 if the set that we're talking about is A, B, C, D, E. That is going to give us the 0 element because the intersection is empty. But notice that the two sets themselves are not empty, which means that those are zero divisors. And it doesn't take much imagination to see that pretty much every element of Pn is going to be a zero divisor, except for 2. The empty set is not going to be a zero divisor because it's 0 itself. And the entire set is not going to be a zero divisor because if you intersect anything with the entire set, the intersection will be the set you're intersecting with the entire set. And so that can only be the empty set in order to get 0. All right, so that gives us an idea of how zero divisors work. Let's see if we can think about how inverses work. Now, just remember, this is how inverses work in general, and we're going to apply that to things like additive inverses and multiplicative inverses. So first of all, in order to have an inverse, you first have to have an identity, and that is the element that leaves everything alone under the operation that you're thinking about. So if it leaves everything alone when you add it, that's an additive identity. If it leaves everything alone when you multiply it, that's a multiplicative identity. Once you have an identity, the inverse of an element is an element that brings that element back to the identity when you do the operation. So for additive inverse, that means you add it to the original element to get you back to additive identity. Or for multiplicative inverse, that means you multiply it by the original element to bring it back to the multiplicative identity. So for a ring, a multiplicative identity, which is also called just an identity, which I hate, or unity, which I hate even more, but nobody invited me to the meeting, so those are the names we're stuck with, is an element of R we denote by 1 sub R, inspired by the number 1, such that for all elements A in the ring, we have A times 1 equals A, and because, again, multiplication might not be commutative, it also has to be true that 1 times A is equal to A. And yes, there are examples of things that aren't of rings where you have it one way but not the other. So let A be an element of the ring. We say that B is a multiplicative inverse of A if when you multiply it by A, you get the multiplicative identity. So that means if you multiply A times B, you get the multiplicative identity. When you multiply B times A, you also get the multiplicative identity. And yes, you have to check both of them. And we call A unit if it has a multiplicative inverse. Very similar as we did with Zn. All right, so we're going to get a taste of how units are by playing with the number 2. And what I mean by that is in different contexts, we're going to see if 2, whether or not 2 is a unit. So we're going to either show that it is a unit or show that it's not a unit. So let's get started. So in the integers, is 2 a unit? Well, we need an integer z such that 2 times z is equal to 1. 1's our multiplicative identity, and we need 2 times z equal to 1. However, 2z is going to be an even number no matter what z is, and 1 is an odd number, which means you can't have an even number equal to an odd number, and that means 2 is not a unit in z. What about in the integers? Or not in the integers, in the rational numbers. Well, in the rational numbers, now you have that 1/2 is a rational number, right? 1/2 was not an integer, that's why we had trouble with z. And notice that when you multiply 1/2 on both sides of 2, 2 times 1/2 or 1/2 times 2, you get 1. That means 2 is a unit, and by the way, so is 1/2, right? Because it has a multiplicative inverse, 2. What about z10? Well, in z10, we're going to have issues, right? Can we have the bracket 2 times bracket z equal 1, where bracket z is some integer, right? Can we multiply 2 congruence classes together to get the congruence class of 1? Well, let's see. If I multiply the congruence class with 2 times the congruence class with z, you get the congruence class with 2 times z. And in order for the congruence class of 2 times z to equal the congruence class of 1, that means that 2z has to be congruent to 1 mod 10. What does that mean? That means that 2z is equal to 1 plus a multiple of 10. And once again, on the left side, you have an even number, 2z. On the right-hand side, you have an odd number, 1 plus an even number, 10k. And so that can't happen, which means that 2 is not a unit. What about z5? Well, z5 is a little nicer. If I take 2 times 3, I get 6. But 6 is the same as 1. And so that means 2 is a unit. All right, so now see if you can get some experience working with zero divisors and units on the PDF file that's included with this video.